Okay, this question is asking us whether these pairs are actually resonance forms or something else, maybe different molecules altogether. And so let's just see what happens if we want to go from let's see here, from this one to this one in problem A. Now, we can write a curved arrow or a path of curved arrows that bring us from this structure to this one, but this breaks one of the rules of resonance, which is it breaks a single bond here. So we could write this set of curved arrows that go from here to here to here to here. And actually that is a chemical reaction because it involves the rearrangement of essentially of the carbon skeleton. So in this structure, the distance between these two carbon atoms is actually quite a bit longer than the distance between the carbon atoms in this structure. So this actually represents a chemical reaction. It represents a change in the location, the relative position of the nuclei. And that is essentially what a chemical reaction is. So these are not resonance forms because they break a single bond. So let's look at B here. So we have an oxygen with 3 lone pairs and a negative formal charge next to a pi bond. And so when you have a situation where you have a lone pair next to a pi bond, you can draw a resonance structure that moves a lone pair into forming a pi bond, and then the pi bond now has to go to form a lone pair. And so notice how these arrows are very specifically drawn. I'll draw them again so you can see. The lone pair, it could be any lone pair, it could be this one, doesn't matter, it could be this one. But the placement of the arrow is very important. So the tail has to start at a lone pair and be placed into where the pi bond, now the new pi bond is. So notice that here we have 3 lone pairs, and now in the second resonance structure we have 2 lone pairs. Here we have a single bond, and here we have a double bond. So one of these lone pairs goes into forming this double bond. We can't stop there because otherwise we would have a Texas carbon here, 5 bonds to this carbon. So we have to make room for this pair of electrons by putting this pi bond onto this carbon. So again, a curved arrow with a double-headed, not one of these single barb arrows, but a double-headed arrow always represents, I shouldn't say a double-headed arrow, a real arrow with that's not a fishhook type arrow. This type of arrow where you have a tail and a head. The tail starts at the pair of electrons. In this case, it's the double bond. It's indicating the double bond. You don't have to actually go all the way to the double bond. You can, that's okay too. The tail starts at the pair of electrons, and the head is where the electrons end up, which is here in this lone pair on this carbon atom. So that's a very specific way of drawing curved arrows, and it's the only right way to do it. And these are resonance forms because you're only moving electrons. So resonance forms are 2 structures, 2 Lewis structures. Resonance forms are Lewis structures that differ only in the placement of electrons. And we're talking about lone pairs and pi bonds. Lone pairs pi electrons and pi electrons. So let's do another one here. Let's look at this one. So again, we have an oxygen with 3 lone pairs and a negative charge. Here we have an oxygen with a double bond, and then another lone pair, a pair of electrons in this pi bond. Now this pi bond is gone in this structure, but there's a lone pair here. So we can draw two curved arrows that represent the same movement of electrons. So I'm drawing the curved arrows like this. I could have drawn them like this. I could draw them like this. Well, that's kind of awkward. But any way you want to show how the electrons get there, it could be like this. That's a little bit strange. But you're just showing really a curved arrow usually has just one curve in it. It's not an S shape like this. So if you can draw the arrow, you can draw it like this as well. But it has to show the origin, the tail at the origin of the electrons. In this case, it's a pi bond, going to where the electrons end up, which is in a lone pair on the carbon. So these are resonance structures because they differ only in the placement of lone pairs and pi electrons. Okay, so how about this one? Well, we have another situation where we have an oxygen with 3 lone pairs, but now look at this in the other resonance structure. We have this lone pair and a negative formal charge on carbon, but it's down here at the other end of the ring. But we also have pi electrons that are next to each other. And remember, if you have pi bonds that are next to each other, these 2 pi bonds are on carbons that are adjacent to one another, then you can rearrange those in resonance structures. So if we draw this lone pair, one of these lone pairs going there, and this pi bond going, now there's a new pi bond here where there was a single bond here, so we can put this pi bond into that, making a new pi bond here, and then now this pi bond has to make room so it can put its electrons onto that carbon. So now we have 3 curved arrows, and we've rearranged the electrons in these 2 structures, putting the negative charge on carbon. So here we have, on the first resonance form, we have the negative charge on oxygen, and the other resonance form, it's on carbon. And in fact, these 2 structures here, notice that we're starting from the same structure here and here. This suggests that there's a negative charge on this carbon and a negative charge on that carbon. We can continue, we can actually make another resonance structure where let me write it up here. You can draw another resonance structure. So you have oxygen with its 3 lone pairs, and we could do this so that the negative charge, and I'll draw the double-headed arrow here, the negative charge ends up on this carbon. And we have, I'll try to draw this neatly, like this. So notice how we have now 4 curved arrows, but it indicates that in this molecule, showing these resonance structures allows us to predict that there is a negative charge, partial negative charge here, here, and here. Because remember, Resonance structures are not different molecules, they're just different representations of the same molecule. So if I were to draw this molecule called phenoxide, if I were to draw this molecule and ask you where, and that is not a very neat benzene ring, so let me do that again. Where are the sites of negative charge? You can say it's on oxygen because it's obvious from this resonance structure, this Lewis structure, but if you draw these other resonance structures, this one, and this one, you will know, you'll be able to predict that there's a partial negative charge here, a partial negative charge there, a partial negative charge there, and if we just draw these lone pairs, take the lone pairs out, and a partial negative charge there in this molecule. And actually, one way of looking at this is not a good Lewis structure, but you can show that the pi density is totally what we call delocalized through this whole system. But the negative charges are in these spots. They're not here, not there, and not there on that carbon. And we'll talk a lot more about that as we get into the structure of benzene.